Okay, here's a problem, boy on a swing. Basically what's happening is when the angle theta is 60 degrees, the boy is at rest. And the question is, what's the tension in the rope when it gets down, vertically down to the bottom? And what is the speed? Okay, so what we want to do is determine how to solve this particular problem. Count the degree of freedom. It's not a, well, it is I guess a dead giveaway, but it's 1 degree of freedom. And there are no double dot terms given. And so therefore we need a free body diagram, but it just occurred to me now that they're looking for the tension. So that's a dead giveaway. I didn't even need to do this. But anyway, so it's definitely a free body diagram. Also, this is a time spanner. They tell me what the boy is doing when theta is equal to 60, and then sometime later he's at the bottom, and they want to know what he's doing down there. So that's definitely a time spanner. And because it's a time spanner, I'm going to integrate something. Okay, so because it's a free body diagram, I'm going to draw a free body, which is shown here. There's only 2 forces acting on him. There's the boy's weight, which is 60 pounds. That's weight, not mass. And then there's the strings that are, or cords that are pulling him up. There's really 2 of those, and so when we solve for the tension, you want to divide this by 2 because there's 2 ropes there. Otherwise, mastering is going to count it off. Okay, so now after you draw the free body diagram, you need to sum forces. You have to determine what direction to sum forces in. I'm thinking tangent normal because I know the path. It's a circle. You're asking me for speed, and so that tells me that, well, maybe you want to do a tangent normal. So that's what I'm doing. I'm going to do tangent normal. In order to do that, you have to determine the 2 directions. The tangent is in this direction, that the boy is moving downward. The normal then is perpendicular to that up here. We try to, I'm relating the angles, so if the angle theta is shown here, then this little blue guy is also theta, and then that means that this angle right here is theta as well. Okay, so I'm going to simply write the forces in the tangent direction, so that's this one. You have a 60 pounds, his weight, times the cosine of the angle, and that equals mass. Make sure you convert it to mass. Times the speed dot, that's the angular, or excuse me, that is the acceleration in the tangent component. And then you can sum forces in the normal, and you have your tension from the string, a component of his weight, and that equals mass times v squared over radius of curvature, which is 10 feet. Okay, so now I circle the unknowns. There's 2 unknowns. There's t, and there's v dot, 2 unknowns. Question that many students ask is, how come you don't count v as an unknown? Well, because it's a time spanner, and the way you solve time spanners is you integrate. So what am I going to integrate? Well, what I'm going to do is solve for the acceleration term, that's this guy, solve for the v dot, and integrate it to get the v. So that's the plan of attack. That's why I'm not counting v as an unknown. I'm going to solve for it by getting the v dot. Okay, so I have 2 unknowns, 2 equations. I can solve for it. So if you take the top equation, you can write the v dot is equal to this. Okay, I know I'm integrating, and so I'm going to realize that I've got v, I've got time, and I've got theta as the variables. I can't have all 3 of those. I've got to do that funny transformation. So I'm going to do it here. dv dt, that's v dot, and I'm going to put in a d theta, because I want it in terms of the theta, the angle, equals dv dt, right? So I'm just multiplying by 1, and then I swap the denominators as normal. You know, that's what we do. And so the d theta dt is theta dot, and then you have the dv d theta. Now the problem is I have v, I have theta. I don't have any theta dots in the equation, so I haven't quite finished it. So at this point, that's when I realized, well, you know, maybe what I should have done is used r and theta rather than t and n. Oh well, I'll do that on the second page. But I'm just going to blast forward. Basically, the problem that I have is I don't like the theta dot in there. What I would like is I'd like either a V or a theta all by itself or something, but I don't really want the theta dot. So what comes to mind is, okay, I'm going to try and convert that guy into V. So I'm going to write the velocity equation for polar coordinates, r and theta, right? So this just comes straight out of the book. Because he's on a circle, r dot is 0, so this term is gone. And the only thing you're left with is the r theta dot in the in theta direction. So that's the velocity. Speed is the magnitude of that. So speed, little v, is simply r theta dot. So that's what I put in up here. So I'm going to multiply by r, divide by r. And then what you have is this r theta dot term. That guy right there, that's v. So what you're left with is, this is v divided by the r, dv d theta. Okay, now I have v's and thetas only, no theta dots. Okay, so what I'm going to do is I'm going to pull this guy down, follow this line. I'm going to pull him down, and I'm going to write dv dt, that's v dot, this is dv dt. Right? From right here, it's v over r dv d theta. V over r dv d theta equals 32.2 cosine. Equals 32.2 cosine. Now, I can separate the variables. So I separate the variables. I'm going to leave the 10 over here. V dv, integrate 32 cosine theta d theta. Integrate this guy, you're going to have 1/10. V squared over 2 plus a constant, and then integrate the right hand side, you have 32.2 sine of theta. How do you find the c? You find the c the same way you always find the c. At some, in this case, at some angle, tell me what the velocity is, or the speed. Okay, theta is 60, the speed is 0. So, you put in a 0 for v, you put in a 60 for the theta, and you find out that c is equal to 32.2 sine 60. All right? Now, I want to know what's the v, the speed, when theta is 90. Put in a 90. So over here, you've got, on the left-hand side, you have v squared over 20. That's 1/2 times 1/10, right? V squared over 20. This is the c. V squared over 20 plus c equals the right-hand side, when theta equals 90. Okay, just solve for it, you get 9.29. To get the tension, you just grab this equation, pull him down, so I copied it down here, and then you just plug in. So now, when the angle is 90 degrees, you know what the V is, it's 9.29, so you just pop the values in here, calculate it up, I get 76. That's the that would be double what mastering is wanting you to enter, because they say there's there are two chords, and so each chord's going to carry half of that. All right. So now what I'm going to do is I'm going to do it again. This time I'm going to use the r and theta. Maybe I should have done that to begin with. Okay. So anyway, it's the same free body diagram I had before. So the black guys are the forces. This time I'm summing in a different direction. So you have your r and your theta, right? And so you sum forces in the r direction. You have minus t plus 60 sine theta, and that equals mass times, and now you use the uglier formula for the acceleration in the r direction. And then you sum forces in the theta direction, set it equal to mass times acceleration in the theta direction. And then because r is constant, then the r double dots and the r dots are all gone. And so now take the second equation right here and solve for theta double dot. So you get 32, multiply through by 32. Anyway, this is what you end up with. Okay, so I just simplified it a little bit, collect up some of the constants. All right, so now it's a time spanner. I know I'm going to integrate, so I'm going to integrate this thing. So when I integrate it, now I'm going to use that same trick I had before, right? Theta double dot is d theta dot dt, and then because I want theta, not time, I'm going to put in d theta, swap the denominators, switch them, right? And that's d theta dt, that's theta dot, d theta dot d theta, right? So I don't have the problem that I had with tangent normal, because now I only have theta dot and I have theta, no time. So this would be perfect. So I'll go back to this equation. Go back to this equation right here. Theta double dot, I've got that. This is theta double dot right here. Theta double dot is theta dot d theta dot. The d theta comes over here. I'm separating the variables. Integrate. So over here on the left-hand side, plus an arbitrary constant. Integrate the right-hand side. How do you find c? The same way you always do. This time, I want you tell me a theta, and you tell me the theta dot. Okay? So when theta is equal to 60, it's at rest, so the theta dot has to be 0. And that tells you what the c is. Okay? Now you take that c and put it back into this equation. So you have 1/2 theta dot squared plus c, this is your c, equals the right-hand side. And now I put in theta of 90 because that's where I want to find out what the theta dot is. So I find out that theta dot is equal to 0.929. That's not what they wanted. They wanted velocity. So I write the polar coordinates for the velocity. So that's the equation that comes out of the book. In this case, r dot is 0, so that term is gone. R is equal to 10, so this is 10 theta dot is equal to n theta. The speed is the magnitude. So the speed is this number right here, 10 theta dot. So you multiply by 10 theta dot, boom, you get the same number you had before. How do you get the tension? Well, you plug back in up here and solve for the tension. You'll find out it's exactly the same value it was before. Okay, that's it.